For thousands of years, a restless, deep red star has burned in the shoulder of the Orion constellation. The Egyptians tracked its movements, mapping its presence directly into their ceilings. Even without modern physics, they noticed what every civilization since has seen. This star looks different from the others. It glows with an unsettled, flickering red that the ancient world could observe, but could not yet explain. To understand exactly what they were looking at, we have to look at this scale model. If you place Betelgeuse at the center of our solar system, its outer atmosphere reaches entirely past the orbit of Jupiter. You could fit 400 million of our suns inside its volume. It is an old star, burning through its nuclear fuel at a terminal rate. By the 20th century, astrophysicists had built a solid consensus about this star's life cycle. The data told them Betelgeuse was a massive, solitary red supergiant. It pulsed with a steady, predictable rhythm, shedding material from its surface as it slowly marched towards an eventual gravitational collapse. The scientific models were imperfect, but they provided a clear, manageable picture. Astronomers logged the behavior and watched the star, confident they had the final chapters of its existence accurately mapped out. Then came late 2019. Betelgeuse began to dim. Historically, the star showed gentle, predictable shifts, but this was a dramatic collapse in brightness. Within weeks, it lost nearly 40% of its visible light. Amateur skywatchers around the globe noticed the drop immediately. A point of light that had sat among the 10 brightest stars in the night sky had suddenly faded into something unremarkable. You didn't even need a telescope to see that something was wrong. Observatories from Hawaii to the Arizona desert scrambled to aim their instruments at Orion. Social media feeds filled with anxious speculation, and major news outlets began running coverage asking if Betelgeuse was finally about to explode. The astrophysics community was alarmed because their math failed to explain the event. Existing stellar evolution models possessed no mechanisms to account for a massive star plunging into darkness this quickly. The Great Dimming proved that our most watched neighbor was operating outside the boundaries of our best models. We were looking at a star we no longer understood. To find an answer, scientists deployed the James Webb Space Telescope. Operating 1 million miles from Earth in temperatures close to absolute zero, this $10 billion machine turned its highly sensitive infrared array directly toward the fading star. This data visualization shows exactly what Webb found. While our sun routinely blows off parts of its outer atmosphere, Betelgeuse experienced a massive eruption that dwarfs it by a factor of 400 billion. The dying giant expelled a catastrophic amount of super-hot mass in a single violent outburst. As that material blasted into the freezing vacuum of space, it cooled. It condensed into a dense, asymmetrical cloud of solid silicon monoxide dust. That massive cloud acted like a dark curtain drawn across the cosmos. It sat squarely between Betelgeuse and Earth, physically blocking the star's light and causing the dramatic drop in visible brightness. The telescope also detected massive convective plasma cells boiling across the star's surface. These deep internal upwellings are so large that a single one could engulf the entire Earth, pointing to instability deep within the star's structure. Webb gave us the mechanical cause of the dimming, but that only deepened the mystery.
Red supergiants do not randomly expel 400 billion times the mass of a normal stellar storm. Something massive and unseen was driving this violence. In July of 2025, researchers finally published an answer that changed the basic assumptions about the star's nature. Betelgeuse is not a solitary star. It is a binary system. For 10 million years, a smaller, hot blue-white star had been orbiting the red giant. Named Sywara, it remained undetected because it sits 6 magnitudes fainter than Betelgeuse, entirely swallowed by the blinding glare of its enormous partner. Look at this orbital map. Sywara operates on a 2100-day cycle. Roughly every 6 years, it swings extremely close to the supergiant, passing directly through Betelgeuse's extended outer atmosphere. As the smaller star moves through that thick stellar material, Its gravity acts like a spoon stirring a teacup. It creates massive gravitational ripples, dragging stellar gas in energetic wakes, shaping the asymmetric dust clouds and pulling the surface material into those violent ejections. When we overlay the historical brightness data onto this orbit, the synchronization is exact. The mysterious 6-year rhythm of dimming that baffled scientists for decades aligns perfectly with the moments Sywara passes closest to the giant. The global panic of 2019 was misdiagnosed. We were not watching a solo star on the immediate brink of collapse. We were watching the atmospheric collision of two stars locked in a hidden dance. Factoring Sywara's gravitational pull into the math changes the timeline of Betelgeuse's death. The models built without this missing variable were giving us false readings on the star's internal decay. With the companion star accounted for, the immediate threat of a supernova vanishes. The recalibrated clock pushes the eventual explosion out from a few short decades to roughly 100,000 years in the future. When that day finally arrives, the 650 light-years of distance will keep Earth safe from radiation. But visually, Betelgeuse will shine as brightly as the full moon in our night sky. It will cast shadows on the ground at midnight and burn visibly in broad daylight for months. By finally locating the hidden companion, astronomers can now accurately predict the star's true fate. We have secured front-row seats to what will become the most scientifically productive, closely observed cosmic event in recorded history. But the discovery of Sywara leaves the scientific community with a massive problem. Every measurement, pulsation log, and spectral analysis taken of Betelgeuse over the last century is potentially contaminated. We were studying the gravitational influence of a star we didn't know was there. If Betelgeuse, one of the largest and most intensely scrutinized objects in the night sky, could hide a binary companion for 10 million years, our models for thousands of other stars are likely built on incomplete data. Astronomers are leaning into this complexity, re-examining old datasets and building new frameworks for stellar evolution that can accommodate these hidden variables. In the meantime, the interaction of this binary system continues. The iron, carbon, and silicon currently being blasted into space by Sywara's gravitational pull are seeding the Orion constellation, pushing out the raw chemical building blocks required to form future planets. As the James Webb Telescope continues to record every photon, the answers it provides are being outpaced by new questions. Somewhere in Orion, a star is telling us that even after millennia of observation, we are only now beginning to see the system as it actually is.